So what this graph shows is the distribution of Earth's surface elevation. These very high elevations, they are plus 5 kilometers above sea level, and they are quite rare, so they are uncommon, because they are only present in these mountain areas, which are only a very small proportion of the entire surface of the Earth. By far the biggest distribution is this blob over here, which shows all these very low surface elevation data points. And obviously that reflects the oceans, right? So if you look at this graph and you would calculate the average, the mean, then it would be somewhere around minus 2 kilometers, right? So the average surface elevation across the entire Earth is way below sea level, is about 2 kilometers below sea level. And if you think about it, that's sort of what you'd expect, right? Because the oceans are far bigger than the continents. So about 72% of the entire Earth is covered by ocean, and that leaves a minority that is covered by the continents. So it makes a lot of sense that the average elevation is significantly below sea level. Now, one thing that is perhaps less intuitive is why is the mode, which means the most common value within a distribution, right? The highest spike in this distribution, which is exactly here. Why is this mode exactly at sea level? That is a very fundamental principle that is not by definition. So this is not what defines sea level. There's a very specific geological reason for this that is very fundamental to understanding Earth science. All the source area, so basically these mountainous regions where there is dominantly weathering and erosion, right? Everything I'm coloring in white now, all of that is being destroyed, so it's being lowered. And everything, so these rivers, they flow from the Alps all the way to the sea. So the river Rhine roughly follows this path. And they will eventually meet the North Sea in this case to form a delta. And a delta is a place where the opposite of erosion happens. We were looking at the source initially, this mountain area. We are now looking at the sink. So we are looking at a place where there's not dominantly erosion, but dominantly deposition. So all this material is being destroyed. So these little tiny rocks, they will break off and they will be moved as sediments down towards the sea by rivers. All of this material will eventually end up in the sea. So in the sea, some new land will be built, which is this delta that I demonstrated earlier. Now, therefore, in the source to sink context, there are two things happening. So erosion is always lowering the land, and deposition is raising the land. So over time, this will have the effect that land will always develop towards sea level. So in the context of this graph, erosion is lowering the land towards zero, and deposition is raising everything that is below zero towards zero. So in both cases, the processes will act to make zero the most ideal surface elevation. Now, sea level obviously is not a constant. It changes through geological time. And what we actually see in the rock record is that this spike, so the mode in surface elevation, shifts along with sea level, right? So during the Ice Age, roughly 20,000 years ago, sea level was about 150 meters lower than it is now. So the spike 20,000 years ago was about 150 meters further down towards modern day sea level. So this spike is sort of always moving back and forth depending on what sea level is doing. So if you're super smart, which I'm assuming you are because you're watching the Geo Show, then you might be wondering, okay, so on Earth we have this sea level, right? We have oceans, so we have oceanic crust, continental crust. But then what does this hypsograph look like in different celestial bodies? So that's what we're going to look at. So the next hypsograph I want to show you is a hypsograph, a surface elevation distribution graph of the moon. Now obviously the moon has no oceans and it has no sea level. And that's reflected in this graph in the sense that it's really a single distribution. right? So it's basically a geologically dead planet. There is no source to sink, right? There are no rivers transporting material. There's no real deposition or erosion in any sense. And all the different surface elevations are basically generated by random impact craters. So the moon has this, obviously this very cratered surface, and it really doesn't have much of a geologic process that is skewing this surface elevation distribution in any direction. So it's just a sort of normal distribution. Another interesting hypsograph is the one from Venus. And it's extremely similar to the lunar hypsograph in the sense that it's a single distribution, right? So again, here we don't really have any major surface building geological processes, right? Other than perhaps impacts that are causing a random distribution of surface elevations. There are no rivers depositing any sediment. There's no erosion. There's no plate tectonics, so it's just a very simple spike that really has no skew, nothing other than some randomness going on. So the next hypsograph will show you why most geologists think that Mars is the most interesting terrestrial planet in the solar system. Which is because Mars does have all sorts of geological processes going on. And that's reflected in the fact that we have, like the Earth, a sort of bimodal hypsograph. So earlier I showed you this delta, right? This place where deposition takes place. And this is something that we've also observed on Mars. So we're now moving to a Martian delta. So this system here, this is believed to be, or believed to have been a river, this little arm thing here. And then that enters this basin where, just like in the Earth, it forms a sort of fan-shaped zone of sediment deposition, which is a delta. Now, because of these phenomena, it is believed that Mars at some point was an ocean world, just like the Earth. But one of the great outstanding questions in this debate is not as to whether Mars has had water, right? So there's a lot of geological evidence in the form of minerals and this delta and all these other phenomenon that Mars had water, like a lot of water. One of the big debates is whether this water was there for an extended period of time. Now, obviously, Mars does not have any oceans today. So you could argue as to how sensical it is to attribute some sea level to the planet as it is right now. But what you can do is you can sort of artificially fill up the oceans on Mars, and then you will end up with some sense of where sea level would be today if there were oceans today. So, and that's basically where this x-axis comes from. And what that shows you is that if you look at the mode on Mars within the hypsograph, that the mode is pretty far away from zero in sea level. So the most common elevation on Mars is about 3 or 4 kilometers above what sea level would be. And according to some, right, it's a bit of a difficult, complicated question, but according to some, this suggests that the Martian ocean was not something very long-lived, right? Not something that has existed for a very extended period of time to give Mars the ability to actually develop this mode centering around zero. So as opposed to the Earth, what we are seeing on Mars is that it's simply a bimodal hypsograph with no source to sink process that is changing the hypsograph. So the rivers and the deltas and the oceans, they existed at some point, but not long enough, and they were not geologically powerful enough to really change the surface elevation distribution in the way that this has happened on Earth. Right, so this is, according to some evidence, that the Martian Ocean was a short-lived geological event. Now, another observation that you can make in this super interesting graph is that it's sort of bimodal, right? So we have this distribution here on the left-hand side, this ocean distribution, which centers around what's called the abyssal plain, right? The most common depth of most oceans is around 4.5, 5 kilometers. And then there's a second distribution which centers around sea level. So one thing you can do is you can separate this into two, which is what I did here. And then you basically have two distributions, one ocean distribution, everything in blue, and one continental distribution. And the main reason that we have this bimodality, so this sort of double spike, is because of plate tectonics. So on Earth, we have different plates, and these plates are floating on an ocean of magma, essentially. And the plates are either oceanic plates, which are made from dominantly basalt, or they are continental plates, which are mostly comprised of granite. And granite has a lower density than basalt. So it's basically a mineralogical distinction. So basalt has more metal atoms in it, so it's denser, has a higher density. And granite has almost entirely silicon and oxygen, so it has a lighter density. And because the continents are so different from the oceans in terms of this rock type, in terms of this mineralogy, we see that the continents are essentially buoyant, right? They're floating higher on top of this ocean of magma as compared to the oceanic crust, which is basalt. So then I guess you can ask the question, why does Mars have this bimodal hypsograph, right? So on Earth, this was attributed to plate tectonics, right, and the different rock types and the oceanic crust versus the continental crust. So in Mars, Mars doesn't really have the same type of volcanism and faults and continental plate boundaries in the way that Earth does. So it is believed that Mars never had any plate tectonics in the same way that Venus never had any plate tectonics. But we still have to deal with this bimodal hypsograph. And this really comes down to just the basic observation that Mars has a bimodal topography. So this is a topographic map of Mars. And you can very clearly see that the southern hemisphere of the planet has much higher elevation, right? All these reds and all these oranges. The elevation on average is far higher than in the north, right? So the entire northern hemisphere is just a lower elevation than the south. So here, this little projection here on the right, I think is very clear. So it's a polar projection where the northern circle is the northern hemisphere, right? Very low elevation. And the southern circle is the southern hemisphere, which is much higher elevation. And the reason for this is actually unknown. So people are not fully certain why this bimodal topography exists on Mars. Probably the most common interpretation is that Mars was hit by a very, very large meteorite. So somehow there was a giant impact very early in Martian history. And this has, in one way or another, generated a very low topography, a sort of mega impact basin, sort of mega impact crater that essentially covers half of the entire planet. So I hope you learned something this episode. I hope you learned something about hypsographs. And another sort of closing remark is that these are very simple graphs that show you a lot of really, really fundamental principles, right? So source to sink, erosion, sea level. And really, if you want to get down into this, it's a really good starting point to get into this really advanced topics in Earth science. Another thing that this is interesting about these hypsographs is that they are considered by some to be potential tools for exoplanet exploration. Right, so we've learned that there's a lot you can say about the hypsograph, based on the hypsograph, about the geological history and buildup of a planet. So if let's say in the future, if we get even better telescopes, then we might be able to make hypsographs of planets, and that will tell us all sorts of interesting information about this planet, whether it's had plate tectonics, whether it's had oceans or things like that. So I hope you enjoyed the episode. Don't forget to like and subscribe, and I'll see you in the next episode.